Hello, my name is Donald Murta and I would like to introduce you to our atmosphere. To begin with, we will look at how we divide the atmosphere into different layers by how the temperature changes with altitude. Then we will consider atmospheric composition. Following that, we consider what causes the wind to blow and the general wind patterns on the Earth. This figure shows how, on average, the temperature in the atmosphere varies as a function of height, from the ground up to 120 kilometers. The lowest layer is called the troposphere and contains approximately 75% of the mass of the atmosphere and 99% of the water vapour. It is characterised by falling temperature by height and extends up to about 8 kilometers near the poles and about 18 kilometers over the equator. The temperature on average decreases by about 6.5 Kelvin per kilometre, reaching a minimum at the tropopause. It is the low temperature at the tropopause in the tropics that limits the amount of water vapour in the upper layers of the atmosphere by freezing it out, whereby it falls back to the surface as rain or snow. Above the troposphere we find the stratosphere, characterised by increasing temperatures. This positive gradient makes the air very stable, with little vertical mixing, leading to its name from the Greek stratos, meaning layered. The increase in temperature is caused by the absorption of ultraviolet or UV light by ozone, and the temperature reaches a maximum at about 50 kilometers above the surface. This turning point is known as the stratopause, and above this we enter the mesosphere, where the temperature again falls with altitude. The decrease is due to easier and easier cooling to space as the amount of gas above decreases. The greenhouse gas carbon dioxide is responsible for most of this. At around 90 kilometers we reach the thermosphere. At this height there is only about 1/1,000,000th of the atmosphere remaining above us, but it is here that the most energetic part of the sun's light is absorbed, and thus the temperature increases again. The solar photons have enough energy to break apart oxygen and nitrogen molecules, as well as ionizing them. I have already hinted at the fact that the air pressure decreases with altitude, and we will now see why. If we consider a cylindrical parcel of air with density ρ, the force it will exert on the parcel below due to its weight is ρg a dz. A is the cross-sectional area, and dz is the thickness of the parcel. G is the acceleration due to gravity. We can see that the change in pressure from the bottom to the top of the parcel, dP, is minus ρg dz, since the pressure is the force divided by the area. If we substitute for ρ using the ideal gas law and integrate this equation, we can see that the pressure decreases exponentially with height, with the pressure at the ground given by P0. The constant h is called the scale height, and means that the pressure reduces by a factor of 1/e for each increase in altitude by h. Using the ideal gas law, we can derive that h is equal to kT over mg, where m is the mass of a molecule, or h is equal to RT over capital Mg, where R is the ideal gas constant, and m is the molar mass of the gas. Since our atmosphere is approximately 80% nitrogen with molar mass 28 grams per mole and 20% oxygen with molar mass 32 grams per mole, we can use m approximately equal to 0.29 kilograms per mole. This leads to a scale height of about 8 kilometers. As I have already mentioned, air is composed of mostly nitrogen and oxygen. The table shows which other gases are present in the air. Argon is the next most abundant gas at about 1%, followed by carbon dioxide that has now reached about 400 parts per million. Another important greenhouse gas is methane, which is present at about 2 parts per million. As you can see, the amount of water vapour varies widely depending on conditions. We have already mentioned that there is ozone in the stratosphere, but only at levels of 8 parts per million. Still, it plays a very important role in protecting us from the solar radiation. The next thing to consider is how composition varies with altitude. In general, the atmosphere is very well mixed, with more or less the same composition up to about 100 kilometers. That is, if we ignore species that are produced in small amounts by photochemistry, such as ozone. The figure shows this, with the atmosphere below 100 kilometers being composed mostly of N2 and O2. Above 100 kilometers, several things happen. One is that the UV light that heats the thermosphere has started to break down oxygen molecules into oxygen atoms, O. The other is that the turbulence that has kept the atmosphere well mixed can no longer be maintained, since the distance between molecules in this very thin gas is now too great. This means that the heavier and lighter gases separate, with the heavier ones below and the lighter ones above, just like oil on water. Above 500 kilometers, what atmosphere there is mostly hydrogen atoms. So far we have looked at the static atmosphere. Now we will consider dynamics, or what makes the wind blow. The lines in this plot are supposed to indicate lines of constant pressure, isobars, going from high pressure at the bottom to lower pressure at the top. Obviously an arc parcel will feel a force from high to low pressure. Here is one example of the way such a pressure gradient can occur. We have two air masses. The one on the left is warm air and the one on the right cooler air. The pressure at the surface is the same in both cases. Simply because the warm air is less dense, the pressure falls more slowly with altitude. Or in terms of equations, the scale height is larger for warm air. This means that at a given height, the pressure on the left is greater than the pressure on the right. You can imagine this occurring when warm equatorial air meets cold polar air. The wind blows from high pressure to low, and this is true on the very local scale. However, for larger scale winds, we have to remember that we live on a rotating globe. This introduces an apparent force called the Corioli force. A simple way to consider this is to imagine that you are standing at the equator and throw a ball northwards. Because we are rotating around the Earth's axis, and at the equator we are furthest from this axis, the speed at which we are moving eastwards is larger than for a point nearer the pole. This is illustrated in the upper diagram. So the ball we throw northwards has an eastward velocity that is larger than the surface further north, and therefore will tend to land to the east of the starting point. It will appear to have been pulled eastwards. In the northern hemisphere, this force always pulls to the right of the motion, so that a ball thrown southwards from the pole will appear to move to the west. This is illustrated in the lower diagram. The Corioli force is proportional to the speed, and what happens is that a balance between the pressure force and the Corioli force is set up. The wind then blows along the isobars. The more dense the isobars, the larger the pressure force and the higher the wind speed has to be to balance it. Now we can look at the basic wind patterns over the entire globe. If we begin at mid-latitudes, we see the belt of westerly winds, which are basically driven by the temperature difference between the tropics and the polar regions. The different direction of the temperature gradient and the Corioli force in the northern and southern hemispheres leads to the same westerly winds. Now, in the tropics, where the heating is strongest, we see a rising motion over the equator, or more exactly, the intertropical convergence zone, which tends to follow the sun north and south in the respective summer seasons. This means that the Earth flows poleward at higher altitudes nearer the tropopause and returns near the surface. The different sign of the Corioli force leads to the northeasterly trade winds in the northern hemisphere and the southeasterly trade winds in the southern hemisphere. The region where the air descends near 30 degrees north and south is a region of high pressure with clear weather as the descending air warms and evaporates any cloud. It is also a region of low wind speeds known as the doldrums and feared by sailors. This circulation pattern with rising air near the equator and descending air in the extratropics is known as the Hadley cell. You can see similar cells at other latitudes. This lecture introduced you to the basic terminology used when talking about the atmosphere. I hope it has also excited your interest to learn more.